All right, everyone, welcome back to Étale Homology on October 13th. So previously we were talking about purity and the Gyson sequence. So let me remind you what the goal, what the theorem we were trying to understand was. So we introduced this notion of cohomology with supports. So that was the derived functor, the right derived functors of taking the cohomology of a sheaf and looking at the section supported on a closed subscheme. And then we were trying to understand that functor in the case where the subscheme was smooth inside of some smooth ambient variety. So here's the situation. So z inside of x is this is a closed immersion of k-schemes, and x and z are smooth, and z is of codimension c in x. Then the claim was that for f, locally constant constructible, we have that h of r minus 2c of z with coefficients in a twist of f. So here this means tensoring with the Cth tensor power of the of mu n, where n is something divisible by the torsion order of z, and tensoring that to the minus c and tensoring it with f. So the claim was that there's a canonical isomorphism like this between this group and the Artin cohomology with supports in z of f itself. Okay, so what you should think of is you should think of this as a computation of this group. And this is an isomorphism for for all r. All right, so we did an example of this. We computed the case of a point inside of the affine line. So z is a point and x is the affine line, and f, I think, was the sheaf mu n, maybe. And now I want to explain to you why this theorem is useful, and then I'll say a bit about the proof. But before I do that, are there any questions about the theorem itself? And I think maybe I claimed something like this was telling you something about the cohomology of a deleted neighborhood of z, maybe morally. And I'll also, I think what I sketch of the proof will indicate, at least in part, why that's true. All right, so let me explain now the main corollary of this theorem, which is the existence of a Gyson sequence. And I'll remind you a little bit about what that sequence says in topology also. So suppose I have x and z as above, and u is the open complement of z. Then, first of all, there's an isomorphism for, let me write it this way, for 0 less than or equal to r less than 2c minus 1, there's an isomorphism, well, the restriction map, from the cohomology of x, with coefficients in f as above. So here f is LCC, and of order prime to the character. Sorry, in both of these theorems, maybe for the whole day, I'm going to say f has order prime to the characteristic, meaning the stalks of f have order prime to the characteristic. So here f is LCC. So then there's a restriction map from the cohomology of x with coefficients in f to the cohomology of u with coefficients in f. And in this range, so for small r, this is an isomorphism. And then what happens for big R? There's a log exact sequence going from starting at h2c minus 1 of x with coefficients in f. Then going to the same with u. So this is the first spot where the previous map is not an isomorphism in general. And then what's the co-kernel? It's h0 of z with coefficients in f twisted by minus c. Okay, and then we keep going. We get h2c of x with coefficients in f, going to h2c of u with coefficients in f, and then going to h1 of c with coefficients in f twisted by minus c, and so on and so forth. Okay, so this last sequence is called the Gyson sequence. So what is this saying? It's saying that if you delete something of high codimension in x, then the low degree cohomology of x is the same as the low degree cohomology of the thing you deleted. And there's a long exact sequence which relates the cohomology of x, the cohomology of the complement, and the cohomology of the open, and the cohomology of the closed complement, but in different degree. Okay, so we're going to deduce this from this theorem. This theorem is called purity in a second, but let me just tell you a little bit about what the topological analog is. Well, before I do that, are there any questions about this corollary?
Can you see why it's called purity?
Why is this called purity? It's saying, yeah, so it's kind of because of this corollary in the first half of this. So what it's saying is that the cohomology of high codimension stuff doesn't matter. In other words, it's supported purely in low codimension. So that's the reason. And there's a long tradition of theorems like this. So maybe one of the earliest examples is the Zariski-Nagata purity, right? Have you seen this, Arvind?
The branch locus?
Yeah. So that's purity of the branch locus, which says that if you have a nice scheme, like a normal scheme, in an Étale cover, the branch locus is concentrated in codimension 1, right? And what that's saying is it's the analog of this statement for H1, in fact, right? It's saying that covers, so H1 is torsors. So if you put a constant group here, that would be like G covers. So it's saying those only depend on codimension 1.
Cool, thanks.
Yeah. In other words, if you delete a codimension 2 thing, covers don't change. Yeah, so that's actually, this Zariski-Nagata purity is, well, and for kind of non-abelian coefficients, exactly this statement. For C is at least 2, and R is 1. But then there's a lot of, this is a very long story, and this theorem is not the end of the story. So, for example, the main question is what happens if Z is, there's a lot of variants of this, but the main one is what happens if X or Z is not smooth. There's variants in flat cohomology where you replace F with like a finite flat group scheme, and that kind of thing. And those result, there's like people working on that now. So very recently, Kostuditz and Schulze proved a very strong purity theorem in this sort of case where F is a finite flat group scheme and you're working with flat cohomology using perfectoid techniques. Okay, so this is something that's not so far from the cutting edge of math research. Are there any other questions before I talk about the topological situation for a minute? Okay, so let me just briefly say what the topological situation is. So I just want to explain what these maps H2n minus 1 of U with coefficients in F restricted to U to H. Sorry, let me do it this way. H2C minus 1 plus I to HI of Z with coefficients in F minus CR. Does anyone know? I'm curious. Yeah, so what you do is what you do is you take Z tilde to be a deleted neighborhood of Z. So what this means is you take a small epsilon ball around Z and then delete Z. So that's a sphere bundle over Z, right? That looks like you took the normal bundle of Z and deleted the zero section, which is homotypic to a sphere bundle. So there's this map pi Z tilde from Z to Z, from Z tilde to Z rather, which is it's homotypic to a sphere bundle. And now if you stare at the Lorentz spectral sequence for a map like this, so for a sphere bundle, what it'll just, you'll get two columns which are non-zero, and then everything else will be rows. That's just because the cohomology of a sphere is non-vanishing in exactly 2 degrees. And so what that means is that there's only one page of the spectral sequence where the differentials can be non-vanishing. And okay, I mean, you're going to have to trust me on this, but unwinding this, what you get is a map. You get a Longzaf sequence, which looks like H2C minus 1 plus I of Z with coefficients in F goes to H2C minus 1 plus I of Z tilde with coefficients in F. And this goes to HI of Z with coefficients in F, and then you get a map to H2C plus I of Z with coefficients in F, and so on and so forth. Okay, and so here, this really requires that F be defined on all of X, not just on U. Okay, and so what is this map? This map is one of the differentials from the Lorentz spectral sequence. Okay, and then what's our map from U to Z? Well, there's just a restriction map from H2C minus 1 plus I of U with coefficients in F to the cohomology of Z tilde. Okay, so this is this lower sequence here is called the in topology it's called the Gysin exact sequence. And what we're doing, and this is kind of the historical motivation. So what purity and this Gysin sequence above are doing is it's telling us how to get this kind of exact sequence when we can't take deleted neighborhoods and look at sphere bundles and stuff. Like that's not something that really makes sense in algebraic geometry, although we'll see in a little bit that like morally it is kind of what's happening. All right, are there any questions about this topological analog? Okay, so this is what you're supposed to think is that what we're doing is, yeah, I mean, another way of describing this map is if you've, so this map here, this is what I call delta, is if you think about things in terms of de Rham cohomology, maybe this is the easiest description, then this thing is it's like 2C minus 1 plus I forms. And what's this map down? Well, how do you go from 2C minus 1 plus I forms on a sphere bundle over something to I forms on the base? You integrate the forms along the fibers. So that's what this map is. It's integration along fibers morally. All right. Are there any questions about that? All right. If not, let me maybe copy the statement of the theorem down so that we can look at it when we prove it. All right. So can anyone help me? So let's prove. So prove that the theorem, so purity, implies this corollary above. So can anyone tell me how to do it? So what did purity do? It gave us a way to compute cohomology with support. So somehow we're going to have to use that, right?
There's a long exact sequence from cohomology with support to cohomology on X to cohomology on U.
Yeah, exactly right. So we just in the long exact sequence for cohomology with supports, we just replace HZ with h in the appropriate degree of z with coefficients in f twisted by minus c. Okay, and that's the whole proof, but let's just think about it in a little bit. So what are we getting? So first of all, we wanted to prove two statements. So we wanted to prove there was some isomorphism in low degree. Well, where does that come from? That just comes from the fact that if R is less than 2c, then this group is just 0, right? Because R minus 2c is negative. So then we get a Longzaf sequence relating this and this, where the stuff on the two sides is just identically 0, right? And that's why there's an isomorphism. And then over here, this is what you get just by literally replacing in the Longzaf sequence for cohomology with supports, replacing cohomology with supports with what you get out of purity. All right. Are there any questions about that? All right. So let me do an example now. And I'm gonna have to owe you something in the example, but not too much. So what I want to do is compute the cohomology of projective space. So using this long Gyson sequence. All right. So first of all, step one is what's the cohomology of A1? So let's compute the cohomology of A1 with mu n coefficients. So can anyone tell me what it is? And here I'm going to assume, as I will throughout this lecture, that n, that the characteristic of the ground field does not divide n. So can anyone remind me what is the cohomology of the affine line? Anyone?
Is Z mod NZ for I0, and then I think 0 for I1.
Yeah, so for I0, so with Z mod NZ coefficients, it would be Z mod NZ with mu n coefficients, it's mu n. Maybe, let me just be clear, I'll say K is algebraically closed. And then it's for I bigger than 0, it's just 0. And why is that? Well, we had this Longzaf sequence from the Kunis sequence, right? Which said that we had relating the cohomology of mu n to the cohomology of GM. The cohomology of GM vanished in degree bigger than 1 and was just pick in degree 1, and pick of the affine line is 0. So that's why. Okay. So then 2, and this I'm going to have to owe you. I'm going to sketch the proof of the Kunis theorem in a couple lectures, but there's a Kunis theorem that lets us compute the cohomology of a product, and what this implies is that in fact the same thing is true for the cohomology of affine space. So there's a little subtlety here I'll talk about when I get to the Kunis theorem, but we get the same computation. So it's mu n for I equals 0 and 0 for I bigger than 0. And by the way, I mean, this should be familiar to you guys, like the affine space over the complex numbers is contractible, right? Okay, now finally, let's compute the cohomology of projective space. So can anyone tell me how to do it?
We could use the Gyson sequence plus the previous computation for an open.
Great. So I guess what pair should I use the Gysin sequence for?
AN and PN.
Yeah. So maybe PN minus 1 and PN because the pair is the closed thing.
Yes.
So we're going to use the Gysin sequence for just PN and PN minus 1. And what does that give us? So here C is 1, right? The codimension is 1. So we get that HR of PN with coefficients, say in let's just say Z mod NZ is equal to HR of affine space with coefficients in Z mod NZ for 0 less than or equal to R less than 2C minus 1 is just 1. So that's for R equals 0. Okay, great. That wasn't so bad. And then we get a long exact sequence, which goes from 0 to H1 of Pn with coefficients in Z mod NZ to H1 of affine space with coefficients in Z mod NZ to H0 of Pn minus 1 with coefficients in Z mod NZ of minus 1, right? That's let me actually just write it that way. Maybe it would actually be a little bit easier if I do mu n here. Yeah, let me just do that. So I'm going to do mu n here, and then here we'll get just Z mod NZ. So mu n twisted by minus 1 is just Z mod NZ. And this goes to H2 Pn with coefficients in mu n. That goes to H2 of An with coefficients in mu n. That goes to H1 of Pn minus 1 with coefficients in Z mod NZ, and so on and so forth. Okay, great. So now what? So what we get is that for excuse me, so we get H1. This immediately tells us that H1 of Pn mu n is equal to 0, and that Hi in general of Pn with coefficients in mu n is isomorphic to Hi minus 2 of Pn minus 1 with coefficients in Z mod NZ. For I at least 2. All right, now what?
Induction.
Yeah, so now we use induction on n, and the output is that that HR of Pn, and let me just phrase things with Z mod NZ coefficients, is going to be Z mod NZ twisted by negative R over 2 for R even, and 0 otherwise. And here R even and less than or equal to 2n. Great. Are there any questions about that? Cool. All right, so we computed the cohomology of projective states modulo this Kunis computation, which we'll do later. You could also, I mean, honestly, you don't really need Kunis here. So if you worked a little bit harder, if you computed the cohomology of affine space over a strictly Henselian local ring, you could use the Luray spectral sequence for the map from An to An minus 1. But we haven't computed the cohomology of affine space over a strictly Henselian local ring. Sorry, I saw, Arvin, that you unmuted. Did you have a question?
We can discuss it later. Maybe it's just about what does that look like, the negative R over 2. I understand it changes the Galois action, but
That's right. Yeah.
I don't have a concrete example in mind.
Oh yeah, I can make that very concrete for you. So let's just say, what is Z mod NZ of minus 1? So that's just the dual of mu n, right? So that means you're asking via the dual of the cyclotomic character. So for example, if you have a Frobenius, well, it depends whether you're working with arithmetic or geometric Frobenius, but depending on which one you do, it'll be just multiplying by q or 1 over q, right? And then okay, well, what if you, instead of minus 1, you have minus 5? Well, then it would be q to the 5th or q to the minus 5th. Does that help, Arvin?
Yeah, I think that helps a lot. Thanks.
Okay, great. All right. So now let me sketch the proof of purity. So this is just a sketch. And we'll see at some point we reduce to a situation which is, it looks a lot like a sphere bundle over some base, which is, I mean, that's why I kind of explained the topological analog earlier. Okay, so what's the situation? So we've, as usual, U goes into X via some open immersion J, and then Z is X minus U is the closed complement, and that's embedded via some immersion I. And so step one is to reduce to a local statement. So this is I mean, somehow this is what you always have to do when you want to prove a general statement like this in Étale homology. Like, you cannot compute with an arbitrary smooth pair even. What you have to do is get into a situation where you can compute, namely a smooth pair that's very concrete. So in order to do that, we need a local statement, and right now the statement we're trying to prove is not local. So what we're going to do is we're going to make a definition. So I'm going to define I upper shriek of a sheaf F, as in the statement of the theorem, to be the following. So it's the pullback to Z of the kernel of the natural restriction map from F to J lower star of J upper star of F. Okay, so what is this map? It takes a section of F and then it restricts it to its value on U. Okay, so this is a sheaf on Z, and people call it I upper shriek, but what is it? It's taking the sections of F supported on Z. So as we'll see in a moment, this is a kind of local version of taking global sections with support. Are there any questions about this definition?
Excuse me, the first J, is it a lower star or a lower shriek?
That's a lower star.
Thank you.
Yeah. If it was a lower shriek, then I think you would just get 0. Or no, sorry, then you just get I upper star of F. Sorry. Yeah. Sorry, was there another question?
Is this related to like Grothendieck upper shriek?
Yeah, so I was going to say that. So it's not quite Grothendieck upper shriek. So Grothendieck upper shriek is about Grothendieck duality, which is about coherent sheaves. So this is related to the Verdier upper shriek. So there's a similar story to Grothendieck duality for constructible sheaves called Verdier duality, or Grothendieck Verdier duality, I guess, in the Étale setting. And this is a special case of the upper shriek functor from Verdier duality. Does that answer your question, Ben?
Is it usually defined at the level of sheaves or a derived category of sheaves?
Yeah, so in general, it would be defined on the derived category. And we'll see that this I upper shriek is not exact in a second. So in fact, it has derived functors and so on. I mean, that's not totally obvious, but I'll state a theorem that implies it. But I mean, because we're in this nice setting of a closed immersion, it's very easy to define H0 of I upper shriek.
Okay.
And that's why I've done it this way. Yeah, and when you prove, I mean, like the stuff I'm proving today is like stuff you have to do when you prove Verdier duality in general. So this is a step. I mean, there's no like highfalutin way to avoid this that I know of. Like, you have to do some stuff with actual sheaves. Does that answer your question, Ben?
Yeah.
Great. All right. So let's what we're going to do is study this functor a little bit and use it to give a local version of the statement we're trying to prove, which will then imply the global version. So first of all, let's just try to understand where this comes from. So if you've seen Verdier duality before, has been asked about, then maybe the following statement won't be so surprising. So the statement is that I lower star is left adjoint to I upper shriek. So I think this shouldn't be so surprising. So we knew before that I lower star had a left adjoint, so namely I upper star. And now we know it has a right adjoint, I upper shriek. And that's not surprising, I think, because I lower star is exact. And I'm going to leave the proof of this adjointness as an exercise. It's not very hard, but you should do it. Just prove it by hand.
Sorry, can I ask one more question?
Yeah, go ahead.
So that's why this thing only exists actually as a functor of sheaves in this setting, because I lower star is exact, whereas it usually
right, exactly. So if in a setting where the push forward is not exact, you can't have a right adjoint. That's right. Yeah, I mean, of course, in general, you can take I upper shriek and then take H0 of it. That's a reasonable thing to do. It'll often be 0. But yeah, I mean, so you can get some kind of functor on sheaves. But yeah, in general, if you don't have a closed immersion, it's sort of not a great idea. Yeah.
Thank you.
All right. So I'm going to leave this as an exercise, which you must do. But then the corollary is kind of nice. So the corollary is that I upper shriek is left exact, just because it has a left adjoint, and it preserves injectives. So it sends injectives to injectives. So the proof is, well, it's formal. So the proof is that it has a exact left adjoint. So having a left adjoint proves that I upper shriek is left exact, and it's a formal fact, which I think I gave as an exercise. Another time we wanted to prove some functor preserved injectives. I think when we showed lower star preserved and push forward preserved injectives, if you have a left exact left adjoint, then you preserve exactness. You preserve injectives. Okay, so now what's the claim? So this is going to be the local version of purity. So here we're going to let Z, X, and F be as in the theorem, meaning Z and X are smooth case schemes, and F is locally constant constructible on X of order prime to the characteristic, and Z is codimension C and X. Then the statement is that well, first of all, iota shriek is left exact, so we can define its right adjoints. And the statement is that if you take the 2c, sorry, I didn't mean right adjoint. You can define its right derived functors. So if you take the 2c right derived functor of I and apply it to F, then this is going to be equal to iota upper star of F twisted by minus C. And moreover, if you take the other derived functors of F, these are going to be 0 for I not equal to 0 or 2c. I guess actually just for I not equal to 2c. Or R not equal to 2c. Okay, and here for R equals 0, this is clear because F is locally constant constructible, so it doesn't have any section supported on Z. It's locally constant. All right. Do you guys have any questions about the statement of the theorem? All right. Maybe the proof is going to get a little complicated, so maybe now is a good time for a 2-minute break. All right. Well, if there's no objection, then I'm going to mute myself and grab a cup of water during our 2-minute break. And I'll see you guys at 10:15 Eastern. All right, I'm back. I guess we still have a little under a minute before our break is over. So maybe in the meantime, does anyone have any questions for me? All right, so let's continue then. So we just finished step one of the proof. So we've formulated a local version of purity. So far, we don't know that it's actually a version of purity insofar as we don't know that it actually implies the theorem we're trying to prove. So let's prove that now. So let's prove that the claim implies the theorem. So can anyone help me do that? Well, first of all, I claimed to you that that this upper shriek was a version of cohomology with supports, which is one half of the theorem. So let's make that precise. So the claim is that the global sections on Z of I upper shriek of now any LCC sheaf F is actually equal to the section supported on Z of F. So can anyone tell me why this is true?
Because R1 is 0.
Can you say a little bit more?
When you have the long exact sequence, and because R when it's not and not 2C, and you have 0, and
well, somehow you have to use the definition of I upper shriek, right?
mm-hmm.
Yeah. So I don't think you need any long exact sequence stuff here. I think this is just directly from the definition. So what are you doing? So let's go scroll up to the definition of I upper shriek. So you're taking a global section of F on X, which vanishes on U, right? That's what this left-hand side is, but it's also just the definition of the right-hand side, right? So I think that's the argument. Okay, and then two, then what the Grothendieck spectral sequence for the composition of functors immediately gives you then a spectral sequence going from the cohomology of Z with coefficients in RS I upper shriek F and converging to R plus S with supported at Z of F. So another way of saying that is that another way of saying this is that if you're comfortable with derived functors, is that R gamma composed with R I upper shriek is R gamma Z. Okay, and what did we use here? So we used that. So you get the special sequence when you have a composition of functors where the first one I upper shriek preserves injectives. So we used that fact. Okay, now can anyone tell me why the claim implies the theorem?
So the spectral sequence has 2 columns.
I think just one column, right?
Isn't it also in R equals 0?
No, right, because F was locally constant constructible, so I upper shriek of F is just 0.
Okay.
Right, so in fact, the theorem says that it's 0 unless R is 2C.
Okay, so then it's just exactly, you can plug in R equals 2C there.
Yeah, so exactly right. So by the claim, RS of I lower shriek of F equals 0 for S not equal to 2C. So you just get HR of Z with coefficients in I upper star of F twisted by minus C of equals H H R plus 2C of Z with coefficients in F, of X with coefficients in F, but supported on Z. And this is what we wanted to prove. Okay, so that proves that the claim implies the theorem. Are there any questions about that?
Is that in the line above that? Is that an upper shriek? RS?
Oh yeah, sorry, that's an upper shriek. Yeah, sorry about that. Yeah, exactly right. Any other questions? So all we did is we have this Grothendieck special sequence, which was a more or less formal thing from the fact that I upper shriek preserves injectives, and then we plugged in the statement of the claim to that spectral sequence. All right, so finally, what we have to do is prove the claim. And I'm not going to do it in details, but I'll sketch the argument. So first of all, so it's a local claim, right? So it's a local claim. So I claim one can reduce it to a very special situation. You can reduce to the case of the pair AM and AM minus C embedded in it as one of the coordinate hyperplanes. So this reduction is a form of the structure theorem for smooth morphisms. So what the claim is not only is a smooth thing Étale locally affine space, a smooth pair is Étale locally affine space with one of the coordinate hyperplanes. And the proof is just the same as the proof of the structure theorem for smooth morphisms. All right, and then you just do induction on M and C, and we already did the base case. So the base case was M equals 1 and C equals 1, which we already did last time. Yeah, so that was just the case of the cohomology supported the origin of A1. Okay, and now I think you can imagine how to do it in general. I'm not going to do it, but what you can do, for example, is compute with check cohomology and compute by deleting one, like cover by AM minus different coordinate hyperplanes, right? By all the coordinate hyperplanes containing this one, for example. But I'm not going to do it. All right, are there any questions about that?
So the calculation we did last time did assume that the ground field is algebraically closed. Was this just because we only calculated this in this case, or does the theorem also assume that the ground field is algebraically closed?
So this theorem is a local theorem. So it's in this claim rather is a local theorem. So it's insensitive to algebraic to extending to an algebraic closure. Do you agree with that, Niklas? Like if you're trying to show some stuff is 0, for example, so that's something you can check after an Étale extension.
Okay.
Yeah, and then you're trying to check a map is an isomorphism, and that's something you can check after an Étale extension. So let me show you the claim. Yeah. But the original Gysin thing was over an algebraic. The original purity theorem was over an algebraically closed field. But yeah. Here, this statement is that a particular map is an isomorphism. Okay, and I actually haven't defined the map, so this is not a really great claim, but that's something you can check after base change. All right. Any other questions?
So what part of this looked like the sphere bundle thing?
That's a very good question. So it's this pair. So if you think about the quotient, if you'd like, of AM by AM minus C, that's a sphere times a copy of C to the sum power at C to the M minus C or something like that. Oh, good. I got a thumbs up. Great. Thank you, Ollie. Any other questions? Yeah, so you're supposed to think that this, maybe in the case, this is best in the case where C is actually equal to M. So you have the cohomology of AM relative to a point, and that literally is kind of relative to the complement of a point. And that literally is the sphere. Are there any other questions? All right, so now, so continuing in our quest for computational tools, I want to now start proving, and I'm going to prove modulo a hard geometric statement, Artin's comparison theorem. So I want to prove some comparison theorems. So in particular, Artin's comparison theorem. The main geometric tool I'll use is an object called an elementary fibration. And so this class and next class will be devoted to basically, I'm going to introduce what an elementary fibration is and then use it in various ways to prove, for example, Artin's comparison theorem, which compares Étale cohomology to singular cohomology. And then I'm going to also prove some finiteness theorems for Étale cohomology using it. All right. Are there any questions before I go on?
Is this related to the pencil stuff?
What is the pencil stuff?
Or like you sort of think of like, instead of thinking about like computing the cohomology of a high dimensional thing, you try to look at it over a curve and then.
Yeah, that's exactly the point of elementary fibrations, as we'll see in a second. It's to write everything locally as a curve, as a fibration in curves over a lower dimensional base. Yeah, so maybe let me just give the definition. So this is the definition of an elementary fibration. So it's a diagram as follows. So you have U, which includes into some Y via map J, and then Z is going to be the complement. And this is all over some base S, and I'm just gonna write down a big diagram and then tell you the properties of all the maps. Okay, so you have a big diagram like this, and what are the properties of the maps? One is that J is a Zariski open, is a Zariski open embedding. So U is an open subset of Y. And moreover, it has the property that J of U is fiber-wise dense in Y. So in other words, in each fiber of Y over S, the image of U is dense in that fiber. And then Z is the open complement. And here, let me call this I. I, C to Y is the closed embedding. Okay, 2 is that H is smooth and projective with geometrically connected fibers. So geometrically irreducible fibers. And it has relative dimension 1. So H is a smooth projective curve. And then finally, G is finite Étale. Okay, so in words, what's happened, so we have our open set U, so this is typically the object of interest. And what we do is we write it as an open inside of a smooth proper curve bundle over S. And then moreover, the complement of it is actually finite Étale. It's a disjoint union of Étale multisections. So the key thing about this, is that the topology of the fibers of F are constant. So this is, I mean, a meaningless phrase, but at least over the complex numbers, what this would be saying is that each fiber of this map F is a Riemann surface of the same genus minus the same number of points. So they have the same topology. Are there questions about what this definition is trying to get at?
Just so I understand, it's like we have a family of smooth projective curves, and then we're sort of removing an equal number of points from each fiber.
Yeah, and in a continuous way. So the main thing, and this is really, really key for applications, is that so you remove some multisections. So as you say, you remove some points from each fiber, but those multisections don't ramify anywhere over S. Okay. So the points never collide.
So that means in like prototypically, I mean, S will always be some kind of like affine, some kind of something that's open in a compact.
Well, I mean, S is not super relevant for the picture. You can always just shrink S, and you'll still have an elementary fibration. But S need not be affine in this picture.
Right. I meant that the picture to keep in mind is not like something over P1 or something, because
that's right. That's right. Yeah. I mean, it's very hard to have an elementary fibration over P1. There's not a lot of families of smooth proper curves over P1. That's a good point. Yeah. So in general, yeah, S will be some interest. S can be proper though. I mean, there are interesting families of smooth proper curves over proper bases. Yeah. But the proposition is that, okay, so this may feel like a very restrictive situation, and the kind of important proposition, which is due to Artin, instead it's actually not at all restrictive. So these objects are totally ubiquitous. So here's the theorem. So suppose X is smooth over an algebraically closed field. Then for each point in X, and you can take whatever kind of point you want. It doesn't have to be a closed point, but it'll be enough to prove it for closed points. Then there exists a Zariski open U containing X such that U fits into an elementary fibration. And when I say fits into an elementary fibration, all I just mean is that there exists a Y, S, and Z, and all these maps making a diagram like this. So in other words, one can write in a neighborhood of any point, one can write an open of your variety as a kind of as a fiber bundle in punctured curves. That's what this is trying to say. All right, and I'm not going to prove this theorem because it's geometrically pretty involved. But the idea, at least, is very natural. So you just pick a U. So just pick any nice affine Zariski open. So pick a U, embed in projective space, and then project down. Okay, and if you do this generically and then delete some bad locus, you'll win. Okay, that's not a real proof. I mean, like making it real requires like pretty involved algebraic geometry, but that really is the idea. All right. Are there any questions about the statement?
So the base is spec K bar in this case.
No. So it kind of can't be. So the base S here. The base S here always has dimension 1 less than U, right? Because U is an open in Y, so U and Y have the same dimension. And then this is a curve bundle. So when I say project down, I mean project away from a point.
Mhm.
Yeah. Or project away from a line. Yeah. Are there any questions about that? Yeah, so maybe let me say what I mean. So just project down until the base has dimension of u minus 1. So if you do this generically, the base will end up being well, it'll have a Stein factorization mapping to some open in P dim u minus 1. Does that help, Bob?
Yes.
Great.
So does the choice of u not matter at all, or?
Well, when you do this, you're going to have to delete some stuff. So you'll get a map down, but it won't satisfy all these properties, and there will be some bad locus in the base. For example, where so y is going to more or less be the closure of u. That's not quite right, but it'll be some piece of the closure of u, and then there'll be some points where some place where that's singular, and you'll delete that, and there'll be some places where the complement isn't étale over the base, and you'll delete those, and so on and so forth. And then the main thing you have to arrange is that when you delete those bad loci, like the loci which make you not be in this situation, you have to make sure that you keep x, so that you don't delete x. So the care is doing things generically enough that you can keep x in your open even when you delete all this bad stuff, and arguing that you actually can arrange that. Are there any questions about that? Any other questions? Yeah, so I don't at all. I mean, I think this is maybe calling it a proposition underrates it. It's like I think this was like a big breakthrough when Artin proved this, and it's not an easy theorem, but it's supposed to be like classical algebraic geometry, which is why I'm not proving it. Are there any other questions? All right, so then let me now state the main consequence. And we're not going to be able to prove it today, but we'll, I think, probably spend the rest of our time discussing what it actually means. So here's the theorem. Suppose x is going to be a variety over the complex numbers. And then f is a constructible abelian sheaf on x étale. Then there's three sites that come into play. So first of all, there's the analytic site of x, which I'll define in a moment. Then there's the analytic étale site of x, which I'll also define. And then there's the étale site of x itself. So that's something we know about. And the theorem, first of all, let me give these morphisms of sites names. So this I'll call pi, and this I'll call an. So the claim is that, first of all, pi induces an isomorphism on the cohomology of all abelian sheaves. So in fact, it induces equivalence of categories of sheaves. So for example, if you pull back through pi, you get a equivalence from sheaves on xn to sheaves on xn étale. And then 2 is that that for f as in the theorem, an induces an isomorphism from the Étale homology of x with coefficients in f to the cohomology of this site X and Étale with cohomology in the pullback of F. Okay, and then the corollary is going to be, well, if you go from here to here to here, is that it's going to be that the cohomology of the associated sheaf on the analytic site, and I'll say what I mean by that in a second, is the same as the Étale cohomology of F. Okay, so I have to tell you what these sites are. So first of all, what's Xn? So this is just the usual topology.
Is 2 an isomorphism?
Oh yeah, sorry, it's an isomorphism. Yeah. Thank you. Okay, so what is Xn? So it's the site associated to the Euclidean topology. On the complex analytic space associated to X. So if you'd like, what you can do is locally choose an embedding of X into affine space. So that's given by some polynomials. Those polynomials cut out an honest topological space inside of Cn, and then you locally give it that topology. And then there's a lot of content in checking that that topology is actually independent of your embedding, but that content was worked out in the 40s and 50s. All right, and what is X and Étale? So what is this thing? In other words, there's an honest like Euclidean topological space associated to X, which is locally just cut out by some polynomials in Cn, and the objects of this category are open sets. The morphisms are inclusions, and covers are covers. So what is the analytic Étale site? So this is the category of complex analytic spaces mapping to X. I'm also going to write it Xn, the honest topological space Xn, via local analytic isomorphisms. And then covers are covers. Okay, so what is something that's in the analytic Étale site but not in Xn, like for example a covering space of X is a local analytic isomorphism, but it's not literally an open set in X. All right, are there any questions about the definitions of these sites? So this is just you pretend X is a usual like complex variety and take the underlying topological space and the objects are opens, and this includes things which are local analytic isomorphisms. So for example, covering spaces. So for example, if X is a Riemann surface, like the upper half plane is an object of this site. If the Riemann surface has genus at least 2, like the universal cover. All right, so can anyone tell me, so what is this natural map pi between Xn and Xn Étale?
Every open thing is a local analytic.
Yeah, exactly right. So a map of sites is a functor going the other way, and we just say if we have an open subset of X, that's the inclusion is a local analytic isomorphism. So there's just an inclusion of categories here. Okay, and then what is this map with this functor? Well, it's just you take a variety, an Étale morphism to X, and you analytify it. You take the associated complex analytic space. All right. Are there any questions about that? And then the claim, the fact that this is actually lands in the appropriate category, says that if you have an Étale morphism to X, then its analytification is a local analytic isomorphism. All right. So are there any questions about the statement of this theorem? So what's the main? Let me state the main corollary. So the main corollary is that for F as in the theorem, there's a canonical isomorphism between hi of X Étale F and hi of xn, and then what I'll call fn. So what is this? So what is fn? So you start with a sheaf here, you pull it back to here, and then you push forward to here, for example. But I claimed that pi induces an equivalence of categories between sheaves here and sheaves here. So you just, fn is just the associated sheaf here. But you can think of that as the push forward if you want. It's the same thing. And because pi upper star is adjoint to pi lower star, if pi upper star is an equivalence of categories, then yeah. Then pi lower star has to be the inverse. All right, are there any questions about the statement of the theorem?
So is there some sort of Riemann existence theorem for?
Yeah, so we're gonna have to use the Riemann existence theorem to prove this.
But so won't that give you something stronger than just an isomorphism and cohomology? Won't that give you like almost an equivalence of categories, but under an?
I mean, I don't think so. You'll get something like that for locally. So this is for this is a statement about constructible sheaves. So you would have to make sense of what it means to be a constructible sheaf on the analytic Étale site. And at least for the reasonable notions of that I can think of, it won't be an equivalence of categories because they're kind of like, there are like a lot of closed subsets here that are not closed, that are not Zariski closed.
I guess I'm thinking.
So for LCC sheaves, for locally constant constructible sheaves, then there will be an equivalence of categories.
Okay. Yeah.
But that's not stronger. Like that doesn't imply anything about cohomology, because the category of, if you just take like locally constant constructible sheaves and think about X in that category, that only picks up cohomology of the fundamental group.
Right.
Yeah.
I guess that's really what it's really proving is the fundamental groups are the same.
Yeah, and I'll state, so my plan is after proving this theorem, I'm going to introduce the fundamental group and prove that, well, not quite the fundamental groups are the same, but there's a comparison theorem for the fundamental group, which tells you that at least in
it says that the covering families are the same.
Yeah, the finite covers are the same. That's the key issue. Yeah, and I mean, you have to have some condition like that because the upper half plane is like not algebraic variety. Right. But yeah, that's exactly right. So another way of saying that is that if you allow kind of non-abelian coefficients here, then this is an isomorphism on H1 still. Great. So I'm not going to prove this, and we don't have time to do it today, but I will prove this. So I'll give really most of the proof. I'll prove this for X smooth and F locally constant constructible. Okay. And that will use, so via the theory of elementary fibrations. All right, and I think it is probably best for me to not try to dive into the proof today. What I will say is, so there were two parts of the statement. So one was that this pi induces an equivalence of categories on the category of abelian sheaves or even all sheaves of sets. So one, what I'm going to do is I'm going to leave this to you as an exercise. So this is a purely topological statement. So the content of this is that if you have an analytic Étale cover, you can refine it by objects that actually come from here. So namely just covered by open walls. And that's not so hard. So being a local isomorphism just means that you know, that locally you can find something down here which kind of splits your cover. And that means given a sheaf here, you can get one down here and just explicitly write down an equivalence of categories. So next time I'm going to prove two. All right, in the remaining minute, are there any questions? So two will prove next time. All right, well, if there are no remaining questions, I'm going to stop recording.